Now we'll see deadlock prevention algorithms. Example, let's say you are using 2PL protocol, basic 2PL, otherwise rigorous, otherwise strict 2PL, whatever it is. So that 2PL is going to suffer from deadlock, right? How to avoid that? If you really want to use this 2PL algorithms, then what you do is follow blindly 2PL. But in 2PL, what you do, sometimes when a lock is acquired by some transaction and other transaction asks for that lock, then we are going to block it, right? That is the reason we are getting deadlock. So this time, so in deadlock prevention algorithms, what we do is we just follow basic 2PL followed by whenever you want to, whenever you want to block the transaction, don't always block. Sometimes you block, sometimes you cancel the transaction. In that way, we are avoiding the deadlock. So finally, I will give you overview of this, first of all, deadlock prevention algorithms. So the problem with deadlock, what is the, I can say symptom of deadlock is like this. T1 already we know that holding and waiting, correct? T1 is waiting on T2, T2 is waiting on T3, T3 is waiting on T1. Let's say you get deadlock, right? So when T1 wants a resource which is held by T2, then we block it. Now when T2 wants a resource which is held by T3, we block T2. In that way, every time anybody wants a resource which is held by other transaction, then we are blocking. So when always you block, you get the deadlock. This time what we are doing is only few transactions will be blocked systematically. Who will be blocked and who will be cancelled, I will tell you. Example, let's say if I somehow cancel this transaction T3, then you don't get deadlock, correct? So these deadlock prevention algorithms are going to cancel some of the transactions which are going to form cycle. We'll see why this kind of algorithms work. So I'm going to use these deadlock prevention algorithms along with one of the protocol, otherwise basic 2PL, otherwise rigorous, whatever it is, right? So first of all, we understand these deadlock prevention algorithms and we mix this with 2PL protocols. So wait die algorithm. In wait die algorithm, what is the scenario? First of all, I will tell you. Before going to the algorithm, this is the story. There is a transaction Ti and another transaction Tj. Tj is already holding the lock and Ti wants it. That means Ti wants to have a lock which is held by Tj, and especially that is conflict lock. That means example Tj is having exclusive lock, Ti wants exclusive lock or shared lock. If Tj has shared lock, then Ti wants exclusive lock. Such a situation it is. In that situation, then usually what you do according to basic 2PL or whatever the 2PL, it will block the transaction, correct? But rather than that, we apply this algorithm. That is the only difference. So now we will see the algorithm. First of all, we compare timestamp of Ti and timestamp of Tj. That's why these deadlock prevention algorithms are using timestamps. So we know what is the concept of timestamp, right? Let's use it. Example, your timestamp of Ti, which is going to ask for a lock, like which is asking a lock, right? So that number is, let's say, 10, and let's say this condition is satisfied, then timestamp of Tj should be something around 20. So you just try to understand what is the meaning of 10 and 20 here. 10 is older transaction, 20 is younger transaction. Now, so in this case, really this condition is true. Older transaction is asking a lock which is held by younger transaction, correct? In that situation, in wait die algorithm, what we do is, so this older transaction will wait. That means now this Ti has to wait. Ti has to wait. That is a decision we take. Else, that means what if this condition is false? Recall. Whenever this condition is false, your values will be like this. With Ti value 20, Tj value 10. Now again connect to the story. So Tj is holding the lock. Ti wants that lock. Such Ti's value is 20 and Tj's value 10. Then this condition will be false. Whenever this condition is false, then Ti will become younger transaction and Tj will become older transaction. That means younger transaction is asking a lock which is held by older transaction. In that case, so in this wait die algorithm, will take the other decision. So here wait, right? Then in other case, what happens? Same transaction Ti will die. That means, so else Ti will be aborted. So you know what is the meaning of aborting, right? So aborted and it will be restarted. We will see how this will be restarted with what timestamp. First, let's assume that it will be restarted. So now let's again revise the algorithm. So whenever timestamp of, this is the story of Ti. Ti has to be blocked or killed is the question. So if timestamp of Ti is less than timestamp of Tj, that means the values are reverse. Like timestamp of Ti is 10, timestamp of Tj is 20. That means older transaction wants to request for a lock. Then what we do? We just ask Ti to wait. Here waiting means blocking. That means we block transaction Ti. It's quite normal as usual, right? The second case you see, if the timestamp of Ti is less than timestamp of Tj is wrong. That means if the transaction Ti is younger transaction, then younger transaction will be cancelled. Now in one line, older transaction will wait, younger transaction will be cancelled. That's it. But generally, if you don't use weight day algorithm, if you use basic 2PL, what are you going to do? We are going to always, whenever this kind of situation arises, always we block Ti. But here, rather than always blocking it, if the transaction type we find out, that means is it older or younger than Tj? If it is older than Tj, then it will be waiting. If it is younger than Tj, then immediately that will be cancelled. That is called wait and die algorithm. We will see with an example. This is your schedule. So how this wait die algorithm can be used, we will see. So first of all, let's say your DBMS achieves shared lock on A. We assume like that. Then it will be given because nobody is acquiring the lock, right? So there will not be any problem. Now T2 wants exclusive lock on A. So before that already T1 is using. Let's say at this moment, let's say this transaction T1 has not released the lock. Then what happens? T2 will try to achieve exclusive lock on A. Then definitely, if in usual case it will be blocked, but here it is not the case. We have to apply this condition first. Now we are using wait die algorithm. If it is wait die algorithm, then timestamp of Ti, let's see. So timestamp of Ti is how much? So we are talking about T2, right? 2. 2 less than timestamp of Tj. Who is holding the lock? T1. 2 less than 1, false. That means, so this is younger transaction. Younger transaction has to be cancelled. That's why T2 will be cancelled. So that is what the story. Now after that, so this process will be continued. Then after some time, so T3 gets again right of A. Still T1 holds a lock. Just we are imagining that, let's say still T1 holds a lock. Sir, what if T1 unlocks it? If T1 unlocks, nothing to worry, nothing. So then automatically T3 gets the lock, right? The story is all about what if there is a conflicting lock, correct? That means we assume that, let's say T1 did not unlock it. If T1 has not unlocked it, then here T3, because of T3 what we do? We try to achieve exclusive lock on A, but already now currently T1 is holding the lock. Don't ask me why still it is holding. Maybe see there is a right of A, right? That's why it is still holding. If it is holding, then we are talking about. Then here exclusive lock on A. See the story. Whenever some transaction wants to acquire a lock which is already held by someone, then we apply wait die algorithm to avoid the deadlock. If you don't apply that algorithm, then always your DBMS is going to block it. Then there is a chance of getting deadlock. That story we know already, right? But here, if you use wait die algorithm, what happens? We'll see. Transaction number 3, right? Same story. 3 less than 1. Condition again false. This time again TA will be cancelled. That means this transaction T3 will be cancelled. So in that way, finally all the transactions will be cancelled to avoid the deadlock, right? So this is about deadlock prevention algorithm using wait die concept, right? So here one thing you should understand why this algorithm is going to avoid, otherwise prevent the deadlock. We'll see. If you use this algorithm, so you never get this kind of situation. What is that? T1 to T2, the reason for getting the deadlock, correct? That is, circular wait. T1 is waiting on T2, T2 is waiting on T3, T3 is waiting on T4, and again T4 waits on T1. That is the only reason you get deadlock, right? In that, this situation never arises in this model. The reason we'll ask, Mr. T1, you are waiting on T2, right? Why are you waiting? Are you using wait die algorithm? Yes. If you use wait die algorithm, then this condition should be true for waiting, correct? A transaction will wait only if that timestamp is, that means we know that older transaction will wait, correct? So that means T1 should be older. Perfect. So maybe T1's timestamp we can take 20 and T2's timestamp let's say 30. That's why now T1 is waiting on T2. Now Mr. T4, why are you waiting on T1? The reason is why T4 is waiting on T1 is, see actually, let's take the diagram one more time. So T1 is, let's say, waiting on T2. So T2 is waiting on T3. T3 is waiting on T4. This arrow means, so this left side transaction is waiting on another right side transaction. That is the meaning. Let me follow that. So T4 on T5, T5 on T1. So the meaning of T1 to T2 means, let's say T1 is waiting on T2. So T1 waits on T2 only when the transaction T1 is older transaction, quite obvious, right? Let's fix the values. This is 20, this is 30. Mr. T2, why are you waiting on T3? So T2 will wait on T3 only, the reason is T2 should be older transaction than T3. That's why T3's value should be 40. When the number is more, so definitely it will be younger, right? So same story, T3 versus T4. So then we can take a number 50. Then T4 versus T5, then T5 should be 60, then only T4 will wait. Now we'll ask Mr. T5, are you waiting on T1? Yes. But what is your number? 60. Then what is the number for T1? 20. Who is younger? 60. In our wait day algorithm, T5 never waits on T1. Only olders or elders wait on youngers, but old transaction, here younger transaction never waits on older transaction. That means, so here the case will be cancelling it, correct? So this case, so TI will be aborted. That's why younger transaction will be cancelled. Then you never get deadlock because there is no circle, correct? So that is the way I can prove that wait day algorithm automatically avoids the deadlock. Now we'll see the second case, that is won't wait algorithm. In won't wait algorithm, see the same story but little bit modification. Same TJ is holding the lock, TI wants it, and especially the lock is, I can say that lock is conflicting, right? So in this scenario, the condition will be checked like this. Again, same condition will be checked. If timestamp of TI less than timestamp of TJ, then the case will be here. First of all, we'll see who is younger, who is older. Whenever this condition is true, then the transaction which is our subject, which is 20, let's say, and TJ let's take 30, then only 20 less than 30 true, right? So older transaction, let's say, is wants to acquire the lock in this case. So in this one, won't, this decision is won't. That means we simply won't TJ and we get the lock. We don't wait. In the previous case, wait or die algorithm, when this kind of case arised, we simply waited, correct? This time we don't wait. Then what is the opposite of wait? Won't. That means we have to cancel TJ. Then here TJ is aborted. TJ is aborted and the lock is given to TI, and TI will acquire the lock. Now second case is else. What is else part is, this condition is false. So TI is waiting on TJ and that such TI's value is, let's say, 30 and this is, let's say, 20. 30 less than 20 is false. That means younger transaction, let's say, wants to acquire the lock. What is the case in this one? So second alternative, wait. So TI will wait. Now in one line I can say like this. In this won't wait algorithm, whenever you know the entire story, we are talking about TI now. So TI is younger, then that will be, whenever TI is younger, then that will be waiting, this case. If TI is older, then condition will become true and TJ will be aborted. Understand? So finally, that is the story about won't wait and wait die. We'll try to compare wait die and won't wait. In wait die, so younger transaction die, older transaction waits. In won't wait, again younger transaction wait, older transaction cancels the other transaction. Understand? So in both of them, who is going to be die? See, here younger transaction is going to die. In won't wait algorithm, who is going to die? Definitely younger transaction, because whenever you take the decision won't, so see that case, whenever you are wounding, whom you are wounding? TJ, correct? TJ is aborted. What is TJ situation? We'll see. Whenever this condition is true, let's take TI 20, TJ let's say 30. Then only 20 less than 30 is true, then TJ is aborted. At that time 30 is nothing but indicates younger transaction. Finally, in both of the cases, younger transaction will be killed. What is the reason? Generally in our programming, when you have a transaction with I can say that which is younger transaction. Whenever you have younger transaction, it might have done very less number of instructions, correct? When any transaction does only very less number of instructions, then it is easy to cancel it, correct? But imagine this situation where you are deleting, otherwise aborting a very lengthy transaction which was running since morning. Is it feasible? I mean, is it good idea? Definitely it's not good idea, because you will be wasting computer resources. That's why always we have to delete younger transaction. That is what we are doing in both weight die algorithm, second one wound weight algorithm. That's it. But almost they are quite similar. And one more thing you see here in weight die algorithm, so we are not at all taking the, I mean, example TJ. TJ was holding the lock, correct? That means, so TJ was running on the computer. Then here in wound weight algorithm, we forcefully took the locks from TJ, correct? But here there is no forcefulness here, correct? So I can say that there is a small difference between weight die algorithm and wound weight algorithm. So this weight die algorithm is also known as non-preemptive algorithm with respect to the transaction which is holding the lock. If you see here the transaction TJ which is holding the lock, then that will not be cancelled at any moment. If the older transaction than this transaction comes, the transaction will wait, and if younger transaction than this TJ comes, then that will be cancelled. That's why TJ will not be preempted at any time. That's why this is non-preemptive algorithm. So here if you see wound weight algorithm in that, so transaction TJ will be sometimes cancelled, right? That's why it is a preemptive algorithm. That is one important point. Second important point, when transaction gets cancelled either here or here, then what are you going to do? Then we just definitely we restart it, correct? But with dash. So don't blindly follow the previous technique, right? In the previous technique, we restarted with new timestamp, correct? But here don't restart with new timestamp. The reason is, so why we cancelled the transaction here? The reason is only because it was younger among all, right? So again, if you give a new transaction, that will become younger than the previous transactions value, correct? So that's the reason. If that is the reason, then again it will be cancelled, right? That's why you never do that. So what is the strategy? Whenever a transaction gets cancelled, it's because of its youngerness. Then we have to improve the youngerness. That means we have to make it old. For that, what we do is, whenever we create the transaction again, we have to give some timestamp, right? We give same old timestamp. When you give old timestamp, what happens is, so maybe you take some time to restart it, right? Meanwhile, it will become older, correct? So see the idea. So you have a transaction TI, okay? So TI, its timestamp is, let's say, initially 20. Now let's say it gets cancelled. When it gets cancelled, after some time you are restarting, right? Let's say after some 10 seconds or 15 seconds, whenever you restart it, you have two options. One option is giving same number. I mean, these two are easy options. There might be other complicated options, but one easy option is giving same timestamp 20. Second one, giving a timestamp which is highest at that moment. Example, currently after this transaction gets cancelled, there are a lot of transactions got created. They are up to T70. That means highest timestamp is now 70 in the system. Then you are going to give a new timestamp which is 71. If you give 71, it will become again youngest. Then everyone will cancel it, correct? Because in this weight day algorithm, in wound weight algorithm, transactions with highest timestamp, otherwise youngest transaction will be cancelled easily, correct? That's why to avoid it, because already it got cancelled once, we should do what? Same timestamp we should give. If you give same timestamp 20, though you are, I mean, we are not doing any unfair thing. Why? So when you restart it, by that time, so many other transactions might have come. Their IDs are, let's say, 21, 22, 23, up to 70. Same reasoning will take. So now among them 20 will be the definitely oldest, right? In that way we can understand. So that's why in these algorithms, whenever a transaction gets created again, restarted, so old timestamp we give, so that we are just telling that this transaction is now older than the current existing transactions. Understand? So this is a story about deadlock prevention algorithms.